everyone, welcome to our channel. In this video we are talking about the cross drainage structure. Cross drainage structure is that structure which is constructed at the crossing of a canal or natural drain to dispose drainage water without any disturbance in the canal flow. It's said to be a cross drainage structure. It can be of three types, that is irrigation canal passing over the drainage. The second one is drainage passing over the irrigation canal, and in the third, canal and drainage intersecting at same level. So this one is the cross drainage structure, from where in this direction the canal flow is occur, and from this direction the drain is occur. And this is the contraction zone, and this is the expansion zone, and this is the waterway or the flume portion where the canal is width of the canal is reduced. It's said to be a flume portion. So now let's move to the question. The given question is, design a suitable cross drainage structure from the following data. That is, in the canal section the discharge is 32 meter cube per second, full supply level is 213.5, canal bed level is 212 meter, canal width, bed width is 20 meter, and canal side slope is given as 1.5:1, that is horizontal is to vertical. And in the drainage side, the discharge is 200 meter cube per second, high flood level is 210 meter, and high flood depth is 2.5 meter. This is the world question from PoU in 2013. Now let's start solving this. Here the bed level of canal is at the higher elevation than that of the high flow level of the drainage. So aqueduct should be constructed. So now let's start solving this by step. In first step, we'll design the drainage waterway. Using the Lacey-Rezimi theorem. That is P equals 4.75 root over QD. This is the discharge of drainage, as we have to pass the drainage discharge under the canal in this case. The QD is given as 200 meter cube per second. Equals, on solving this, 67.18 meter. So for this we'll provide 8 clear span of 8 meter each with a 1.5 meter width of pier to pass the discharge of drainage under this length. We'll provide that is 8 times of 8 meter width plus 1.5 times of 7 is because there will be 7 number of pier in between the portion. That is, if this is the contraction zone and this is the flume portion, this is one is the expansion, from here to here there will be, this will be the total length of waterway, and we'll provide 8 meter from here to here. This is 8 meter span, and this is also 8, and similarly the width of this pier will be 1.5. so there will be 7 number of pier. On solving this, the total length will be 74.5 meter. After this, we go to the design of canal waterway, where the given condition is the bed width of canal is 20 meter which is given, but we'll add up 10 meter only. That is, this width we add this section is 10 meter. So the velocity through the drop will be discharge by area. The discharge is given as 32 for the canal. Discharge canal by area canal, that is area is width is assumed to be 10 meter and the depth is given as 1.5 meter. On solving this, the result will be 2.133, which is less than 3 meter per second. The condition satisfied. It means that the velocity of the aqueduct should be less than 3 meter per second. Now let's draw our cross drainage structure. This is the cross drainage structure from where the canal flow occurs in this direction and the drainage flow occurs in this direction to this. This is, let's consider a section 1 at this point and the section 2 at this. This one is the section 3 and this one is the section 4. This one is the length of flume or the waterway length that we have already calculated as 74.5 meter in our first step. Now we will calculate the length of this, which is the length of contraction, and this is the length of expansion. And for the calculation of this length and this length, now let provide display of 2:1 in contraction zone. That is at this. So the length of contraction, this 20 minus 10 is divided by 2 times up to, as the width is reduced from this to this, that is 20 to 10, and the display is considered as 2:1. So this will be 10 meter. And similarly, providing a display of 3:1 in expansion zone. The length of expansion, this one is contraction, and length of expansion will be 20 minus 10 is divided by 2 times of 3 equals 15 meter. This is the 15 meter. Now after this, we go to the design of bed level at different section. In this, first we'll go to the section 4.4. That is, the section 4.4 is this one. And yeah, first we'll determine the velocity at 4 equals discharge is divided by area, where the discharge is given as 32 and area is to be determined for the, so 20 plus 1.5, as the depth is given as 1.5 in question, times of 1.5. On solving this, the result will be 33.375 meter square, or you can calculate the depth of water as FSL, full supply level, minus canal depth. Equals 213.5 minus 212 meter equals 1.5 meter. We have placed this value over here, and now placing this value on this, that is velocity v4 equals 32 is divided 33.375 equals 0.96 meter per second. After this, we'll calculate the velocity at equals v4 square is divided by 2z equals Placing this value is divided by 2 times of 9.1. On solving this, the result is 0.047 meter. In our question, the RL of bed level at section 4 is given. That is RL of bed level at section 4 equals 212.0 meter. That is, this level is given as 212.0 meter is given in our question. So the RL of water surface at 4 will be 212 is this level plus the depth of water is 1.5 equals 0.5 meter. This level is 213.5 meter. The full supply level is 213.5 meter. RL of total energy line at section 44 equals is RL of water level at section 44 213.5 plus velocity head is 0.047 on 213.547 meter, which is the level at this point, that is 213.547 meter. We end up the solution up to section 44. Now we move to section 3.3. For section 3.3 also, we assume the depth of flow equals 1.5 meter, 10 meter. Then velocity at section 3.3 equals 32 is 10 times of 1.5 equals 2.133 meter per second. After this, the velocity head equals v3 square is divided 2g equals 0.232 meter. And after this, we have to calculate the losses of head in expansion. That is, the head loss occur due to the expansion of the canal joint. This can be calculated, losses can be calculated 0.3 times of V3 square minus V4 square is divided by 2G. Placing the value of simply 0.3 times, only have to place the value of V3 and V4. The value of V3, velocity at V3 is 0.232 and the velocity at 4 is, that is 0.047, this value. On solving this, the result will be 0.055 meter. At section 3.3, we have to calculate the level from top to bottom. That is RL of TL at section 3.3 equals RL of total energy line at section 3.3 equals total energy line in section 4.4 plus loss of head in expansion. That is, the total energy line at section 4.4 is 213.547. This value is from here, and equating this, it will be. Now after this, we'll calculate the RL of water level. 3.3 equals RL of TEL at section 4.3 minus velocity head at 3.3. This value is, sorry, this velocity head is subtracted from this equals 213.602 is subtracted from 0.232 equals And at the last, in section 3.3, the RL of bed level at section 3.3 equals RL of water level at section 3.3 minus water depth. Is the RL of water is 213.37 minus 1.5 equals 211.87 meter. So this value 211.87 is the value at this point 7, and this 213.37 is the value at this point, and the total energy line level is 213.602. After this, let's move to section 2.2, where the friction loss in between section 2.2 and section 3.3 can be given as HL equals N square V square L is divided by R power 4 by 3, where N is Manning's coefficient. This can be given as N equals 0.016 for concrete. Then we have to calculate the hydraulic radius R for trapezoidal channel. R equals A by P, where the A is 10.1.5 is divided by perimeter. So now placing all this value on this, that is HL equals 0.016 times of 2.133 square times of L is 74.5, that is we have calculated in first step, is divided by R means 1.154 power 4 by 3 equals 0.072 meter. In this too, we are calculating the level from the top level, that is first we will calculate the RL at TEL in section 2.2 equals RL of TEL in section 3.3 plus head loss in drop. That is TEL in section 3.3 is 213.602. 213.602 is 0.072 equals 213.674 meter. And the RL at water level, RL at in section 2.2 equals RL at TEL, RL at TEL, RL at TEL in section 2.2 minus velocity head at 2.2. As the velocity at section 2.2 section 2.2 and section 3.3 is same, so the velocity head at section 2.2 and 3.3 is also same, that is 213.674 0.232 equals 213.442 meters. This value is already calculated in section 3.3. Now in the next step we'll calculate the RL at bed level at 2.2 equals RL at water level in 2.2 is subtracted with depth of water equals 213.442. This value minus 1.5 is the water depth equals 211.942 meter. Now let's place this value on our figure. That is, this value is the value at this point is 211.942942, and full supply level is this is 213.442, 213.442, and total energy level is 213.674. After this, we go to section 1.1. At section 1.1, the contraction will be occur, so that the head loss in contraction equals 0.2 times of V2 square minus V1 square is divided by 2G. That is, now placing the value 0.2 times of The velocity as v2 is equals to v3, v2 equals v3, and v1 equals v4. We can place the velocity of v3 at v2 and v4 in v1. Now, in this section, we will calculate the level from top to bottom, that is RL of DEL at section 1 equals RL of DEL of 2 plus loss in contraction. That is, the RL of DEL in section 2 is 213.674 plus loss in contraction is 0.037 equals 213.711 meter, and in second RL of water level at 1 equals DEL at 1 minus velocity head at 4. This is equal 4 is equals to v1. And the last RL of bed level equals 664 minus 1.5 equals. So now placing this value on our figure, that is bed level is at this point 2 and 2.164, and full supply level is 213.664, and total energy level is 213.711. So these are all the calculated level. After this, we'll design the transition zone in fourth. In this, we'll design the contraction transition and expansion transition. So contraction transition will be applied on the flow of canal side, incoming flow of canal side, and the expansion transition will be applied on the outflow from canal. This is L expansion, this is L contraction. So first we'll find the width at the contraction transition using Mitra's hyperbolic formula, that is Bx equals Bn dot Bf dot Lf is divided by Bn dot Lf minus x times of Bn minus Bf, where Bn is the bed width of normal section, that is the Bn is the width as this section, and the Bf is the bed width of flume section, width as this section, and Lf is the length of transition with different form from expansion to contraction. This length, and this length, and the Bx is the bed width at any distance x from the flume section. Bx means the width from can be from at this point, this width, or this width at any point from this place. So the for contraction transition, Bn equals 20 meter, Bf equals 10 meter, and Lf equals also 10 meters. So placing this value on above equation, that is Bx equals 20 times of 10 times of 10 is divided by 20 times of 10 minus 10 times of x equals 2000 is divided by 200 minus 10x. So using the heat and trial method, that is, we have to find the value of Bx, placing x, and that is Bx equals 2000 is divided 200 minus 10x. 10x, that is first we'll place the value of 0 on this point. On placing the 0 on this, we'll receive 10, and after this we'll place 2. On placing the 2, we'll receive 11.11, and similarly you can place the 4, 6, but I'll place 8. On placing the 8, it will be 16.67, and placing the 10, it will be 20 meter. From this we can result that at the 2 meter upstream from the flume section, the depth will be 11.11 meter. Similarly, for the expansion transition, the Bn equals 20, Bf equals 10, and Lf equals 15 meter. Similarly, for the expansion transition, as we have done in contraction transition using the Mitra's hyperbolic formula, you can place those value on that formula and find out the required width at the downstream of the flume portion in the expansion section using heat and trial method in Mitra's hyperbolic formula.